السلام عليكم ورحمة الله وبركاته. طبعا اعتبارا من اليوم المحاضرة راح تكون باللغة الإنجليزية، ذلك لأنه حتى تماشيا مع الطالب أو الطلبة اللي ينضمون إلى الكورس اللي هو طلبة من الدول الأخرى حتى يستفادون أكثر من اللغة من المحاضرة هي اللغة الإنجليزية. محاضرتنا الثالثة اليوم اللي هي مادة Advanced Artificial Intelligence، واليوم اللي هو يصادف الأحد 23/2/2025. Good morning everyone. We will begin to the presentation of the first or third artificial intelligence or advanced artificial intelligence lectures for software departments in Wasit University. And today is Sunday, 23 February at 25 years. In the first presentation, the first things of semantics for the predicate calculus. The predicate calculus or the meaning of the semantics, we begin in the introduction of the interpretation. The interpretation, if we use it to the process of semantic, and this is used for main part of the artificial intelligence in the unification process. What's the meaning of the unification and what's the meaning of the interpretation? In the first lecture, we introduced the artificial intelligence. Consists of two main parts. The first thing is the presentation, knowledge presentation. And the second main part is the search process. And we will, in the next lecture, we introduce some types of the algorithms used in the search process. Now, in the presentation, we will introduce the interpretation. What's the meaning of interpretation in this part? We said, for example, when we ask something, for example, let's say, I want to say, when I see something, and after that I ask about this. We begin by interpretation that give the mapping between what I need and the mapping between the knowledge representation. That means get the truth value of the assignment. Let's begin. The meaning of the expression is the truth value assignment over the interpretation. And this go to the definition or main definition. Interpretation is the domain D. The empty sets. And interpretation over D is an assignment of the entities of the D to each of the constant, variable, predicate, and functions of predicate calculus expression such that
Right now, the door is down.
Wait a minute.
Door is
All right. All right. هاي خلصت لنا. For example, this is now a base concept of the family structure. Father, Ali Mona. That's mean Ali is father of Mona. And son, the relationship son between Mona and Sami. That's mean Mona or Sami, son of Mona. An interpretation when I ask something, for example, father X, that's me variable, Mona. When I ask this question, the search began to search this predicate, this is predicate name, and this argument. Predicate calculus, this predicate names, and the argument that brackets between brackets, two brackets. When I ask father, this having two things. The first things make a matching between the name of the predicate, that's name or symbol of the predicate, matching between its name and find that name in the knowledge base. Now found it. First thing. Second thing, that this arguments or its arguments, number of its arguments must match with the same number of the other or that predicate. Now, how many? One, two. Two arguments. Further in the knowledge base. One, two arguments. Now matching. After this process of matching, now we'll give its value. Found, that means true. This is the process of interpretation. Interpretation that assigning value of finding predicates in the knowledge base. When we found it, that is mean true. Not found, that is mean false. When we get the value of the true or false, that means it's interpretation. Now, an interpretation over D. D, that's mean the knowledge base, is an assignment of the entities of D, each type, each element in the D. For example, father, Ali, Mona. To each of the constant. The constant, that means the equations. The father, X, agree. Or variable or predicate and function symbols of the predicate calculus expression. Predicate, variable, and predicate. And constant. Predicate, father. Variable, X. Constant, Mona. each constant is assigned an element of D. Each constant, for example, Mona, is matched with the Mona in the knowledge base, and this is true. This one. Second, each variable X is assigned to an empty subset of D, searching in the D, and matching with what? With Ali. These are the allowable suitable for that variable. Now, each function, this function is our example, each function f of Rtn is defined on m arguments of D and defines mapping from dm into D. dm, that means the arguments of this function. For example, the number of arguments 3. That means D3, power 3. For D, that's all the knowledge. For each predicate P of Rtn is defined on an argument. In our example, P, father. RT, how many of RT in our example? 2. Mona, Ali, and Mona. Is defined on arguments from D. This is knowledge base. Also 2. And defines mapping from Dn, from the answer for the question, into true or false. After mapping, we get either true or false. Truth value of predicate calculus expression. Now we will talk about the truth value. After matching, we get true or false. Assume an expression E and an interpretation I. For example, in our example, E, that means the questions about Father, Ali, Mona. This is mean E. And interpretation, the process of matching and converting into it either true or false. That is mean interpretation. And represented by I. For E over non-empty domain D, domain that is knowledge base, all the knowledge base, D. The truth value of E is determined by. Now, we're talking about the truth value. The truth value, we can get it by the value of constant is the element of D. It is assigned to by I. Now, value of a constant of element D is assigned to by. This is the process of the matching. For what? For the constant. And constant is Mona. Because we ask Father X Mona. Constant Mona. The value of variable in our example, X. Because we ask Father X colon Mona. Is the set of the element of D is assigned by us. And how it's assigned by interpretation? Assignments looking for its value in knowledge base, and after matching we get what? I. Because you ask X, Father X, Mona. And matching X with what? With I. Now the interpretation, I. The value of a function expression is that, not found in our example, is that in the element of D obtained by evaluating the function for the parameters assigned by the interpretation. Now, the value of truth symbols, not found in our example, but for all the information, 3, 2, true, that means T. Or false is mean false. This is the main difference between T capital and the true. T capital means truth value. And the true means symbol. The difference between T and the true, this is a symbol and this is value and the logic value, truth value. Also, false is statement or symbol in the statement. F, that's mean truth value in the logic. 5, the value of an atomic. The value of an atomic sentence is either true or false, as determined by the interpretation. Sentence in our example, or atomic sentence in our example, is the predicate. And what was the predicate? Father X Muna. All this is atomic sentence. The atomic sentence that something cannot be divided in other parts. This is atomic sentence. And in our example, atomic sentence is the predicate. Father X Muna. Atomic sentence is either T or F after interpretation. We get it because it was matching. After matching, because it's D. This is called D. After matching, X has gonna Six, the value of the negation of the sentence is true if the value of the sentence is F, and F is the value of the sentence is true. When the atomic sentence or the sentence is evaluated or interpreted to T, that's mean true, when its truth value is true or false. And it will be false if its real value is negative true. 7, the value of the conjunctions of two sentences is true if the value of both sentences is true, and false otherwise. If one or two are connected by the conjunction and, all the statements will be true when all the elements that are conjuncted by and is true, and will be false if one of this is false. The truth value of the expression using or, imply, and equivalent is determined from the value of their operand as defined in section 2.1. Finally, for a variable x and sentence s containing x, this is quantifier. Now, about the quantifier, when the variable x and the sentence s containing x, now the value of for all x, x where for the statement is true if s is true for all assignment to x under I, and it is false otherwise. What was this meaning? This means that when something, for example, this is x, many variables, and s is the predicate. For example, father x or father Ali, father is x. We ask about whose sons of Ali. Now, x will take many values. This is for all x. It will be true, will be matching all the sons of Ali for this variable x. X will take the value of the names of Ali's sons. This is for all x. And will be true when we looking for all the sum or all the variable that belong to the statement. And this statement was predicate in father, Ali, Farzeh, or comment x. And the quantifier, separate quantifier, that there exists the value of there exists x for the statement s is true, where there is an assignment to x in the interpretation under which s is true, otherwise it is false. And there exists, that means we need to match for only one element. If we get one element, it will be true. Unlike for all that means we must matching all variable. But in there exists need one. If what matching one or get matching one, it will be true. We will define three. A variable is considered free if it is not within the scope of either the universal or existential quantifier. For example, father, or for example, there exists of x, father, Ali, x. Now x inside. Now the scope of for all x as and the father x, the same scope. But when we write for all x father, or for example father, now the scope of the for all x is not contained by the father of all x, because the scope only in this brackets, not also this brackets. And father Ali x, this x not belong to this for all x. This is called free. This is not free because x is belongs to the for all x. And the expression is called closed if all of its variables are quantified. For example, in the father, Ali, colon, x. When we match for all its value and find its value in the knowledge base, matching and interpreted to the x, now called it closed. Because the x matching with all variable and found it from knowledge base. This is closed. Similar relationship between negation and universal existential quantifier are given below. Now we will be looking for the operation of the negation in the quantifier. They exist and for all. And when we put this negation to the, for example, for all, it will be converted to there exist. And the negation of the there exist will be for all. So, for example, now, note there exist for x, not bx. Note there exist will be converted for what? For all x. Note there exist for all x. And note px, not px. And all the statement not for all x, px, not for all would be there exist. And not for this statement px, not px. There exists px. Equivalent to there exists y, by. This is the variable x, the same thing. For all x, qx, the same thing for all y, for qy. For all x, for what? The statement conducted by the and, px and qx. That's mean for all x, px, and for all x, qx, and for all q and x. There exists px and qx. This is the same thing. Q and for x is one. The definition, first order predicate calculus. We were talking about the predicate or the first order predicate. We will use first order predicate because we're talking about the proposition symbols. Proposition symbol, that means in the statements, and we convert the statement to the symbol that represented by capital letter of the English letters. For example, it will rain, represented by the symbol P. We remember that in the second lecture. It will rain, that we represented by symbol it's P. But when we're talking about the P, we can reach its contents. For example, rain, or the day, or for example, it will rain in the Sunday. This is whole component or all the statements represented by the symbol called P. How can I reach its content of this symbol or this statement? I will use predicate. That predicate consists of the relation between object of this statement and represent this relation by predicate, and its arguments of this predicates represent the object of this statement. For example, Ali and Mona. This is object, two objects. And the relation between them, Ali is father of Mona. How can I represent it? Represent by predicate. Predicate the relationship. And the relationship is called father. And the object of two objects, Ali and Mona, represented by arguments. And put it in the two brackets. And separated by the comma. This is called first order predicate calculus, which allows quantified variables to refer to objects in the domain of this course and not to predicates or functions. This is the definition of the first order predicate calculus. Examples of English sentence presented in the predicate calculus. Now we will present some examples that converting from the English sentence into predicate sentence. For example, the first statement, if it doesn't rain on Monday, Tom will go to the mountains. How will we convert this sentence or represent it in the knowledge base by the predicate calculus? Now, the relation, now we can't get the relation whether between two objects, rain and Monday. And the other relation is the go. Go between what? Between Tom and mountains. Tom will go to the mountains. This is now how we get the action about these statements, because this is 22 parts: conditions and action. That means if this is condition. The condition, if not rain in Monday, the action, Tom will go to the mountain. This is meant by imply. And in the predicate, this is a statement. Will not implement it if not, this is true. Must implement this and get through, then go to the second statement. That means when I get this is true, that means rain Monday does not rain because I use not to this statement or this predicate. And not rain, that means not rain in Monday. If it's true, then get tomorrow will go, Tom will go to mountain. The second example, Emma is Doberman, Pinchers, and good dog. We can get two relationships. The first relationship, good dog. For what? For the Emma. That means Emma is a good dog. And is a relation. Emma is a Doberman, represented by the predicate. And the statement will be true when two predicates is true. Two predicates are true. Good dog, Emma, true. And is Emma is Doberman true will be
all the statement will be true. Now the second statement, all basketball players are tall. We can represent it by the conditions and action. The conditions, that means all basketball players. If X, for example, X, and for all X, it will be 3, there will be tall X. That means, in other words, X will be tall if X basketball player. Other example, some people, that means some, not all, some that there exist. Some people like anchovies, relations, the relation person X, there exists someone called X, and this X is person, and this person X likes anchovies. Look, represented, this is statement, and the predicate by this one. There exists X. X means someone. That means there exists someone. And this one is person. And this person like anchovies. Now, if wishes were horses, beggars would ride. That means two relations, equal and ride. Equal wishes and horses. That is mean wishes will be with horses will be equal if, and then ride beggars. That means beggars would be ride if wishes and horse equals. Nobody likes taxes. Relation is like. For what? There exists X, and this X not found. Likes X taxes. Good? Now, we're around to the Block's word, example of semantic meaning. Block word, as we know, consists of the table, and on the table, 4 blocks called A, C, B, D, and R. When we look, as like the human, when we look at about this, we see this. This is 4 blocks, and the block C is over A, and A is over the table, and C is clear, nothing above it, and D is above table, B above D, and B nothing above it, and the R is clear. We can present it or represent it in the knowledge base by using predicate calculus. The predicated relations and objects is the what are objects? A, B, C, D, all these objects. And the relation between them, the relation on something other. The relation, this object is clear, and the relations of the hand is empty. Good? Now we represent this on, for example, on. Which on? On object, on another object. For example, C is on A, B is on D, A is on table, D is on table. On CA. That means C is on A. on B, D, that's me, B on D. On table, A on table. This, and B is on table. And C is clear. B is clear. And finally, hand is empty. This is empty. The following rule describes 12 blocks clear. Now we use the predicate for describing all states of this problem. Now we can use rule, and this rule we use it to the inference rule and the other things. The following will describe when a block is clear. This X and for all X. That means every X. X object. That means every object. Every object X will be clear if X is something above it and nothing, because it's not. That means, in other words, X will be clear if there is not another object called Y will be above X, and written by this form in the predicate calculus. The following rule to define where blocks are clear, and this is block is clear. For example, for all X, for all Y, that means X will be stacked on Y if the clear and empty. That means the hand is clear or empty, nothing in the hand for X, and Y is clear and put down X above Y. In other words, when I want to put something above something other, this is rubber and this is glass. When I could put this rubber above this glass, when it's be clear, therefore must I prove that it's clear first thing. Because it's clear, then I can I put this object above this first object. This is must be clear. This is clear. And what? The hand, it's empty. Now will be it like this. It's empty, and this is clear, and this is clear also. Nothing about this, because this although can't live this, because I must be. This is be clear. And put down. After that, we'll get star X above Y. That means like this. Now, inference rule. Inference rule, the ability to infer new correct expressions from a set of true assertions by using predicates calculus. These new expressions are correct in that they are consistent with all previous interpretations of the original set of expressions. An inference rule, that means when I use inference rule, the first things in the knowledge base must contain some facts, or called in other words, assertions. Must find some assertion that be fixed in the word. It's called facts or assertions. And I will use rule and matching between this rule with these facts, and after I get true matching, I will get a new expression. All this process called inference rule. The basis for verifying the correctness of the truth of inference. The functions of logical inference is to produce a new sentence that logically follow a given set of predicate calculus sentences. An expression X logically follows from a set of predicate calculus expression S if every interpretation that satisfies S also satisfies X. This would mean, for example, that any new predicate calculus expression added to the blocks word must be true in that word, as well as in any other interpretation that the set of expressions may have. When every sentence X produced by an inference rule operating on a set S of the logical expression logically follows from S, then the inference rule is said to be sound. What's the meaning sound? Sound when every sentence X produced by an inference rule operations on the set of S. This is called sound. And if the inference rule is able to produce every expression that's logically from the S, that is said to be complete. When P is rule that's produced everything is called complete. Definition. This so will satisfy, model, valid, inconsistent. For a predicate calculus, expression X and an interpretation I, if X has a value of T, that means X is true. Under interpretation and a particular variable assignment, then interpretation, that means I, is said to satisfy X. This is my meaning of the satisfy. Satisfy if X has a value of 3 under interpretation and particular variable assignment, then I is said to satisfy X. That means is matching between the answer questions and knowledge base when I searching about these questions. If I satisfy X for all variable assignment, then I set model of X. What is the model? Model, that means all things that match it in the knowledge base. When asked some question and I get the answers or all the answers from the knowledge, these answers will be knowledge, will be model. Sure? That model of X. If X is satisfiable if and only if there exists an interpretation and variable assignment that satisfy it. This is satisfiable. For example, when I ask Father Ali Muna and we get matching, that is true, will be satisfiable. But when I ask it about Father Ali Muna are not found, will be not satisfied. This is mean this definition. X is satisfiable if and only if there exists an interpretation. That's mean found. The matching is found. A set of expression is satisfiable if and only if there exists an interpretation and variable assignment that satisfies every element. That is satisfiable. That means when I get the matching, then call this is X is satisfiable. If a set of expression is not satisfiable, what does this mean? Not satisfiable is not matching. It is said to be inconsistent. When this is X, not found in the knowledge base, that is not satisfiable, called inconsistent. Finally, if X has a value T, predicate will be true. For all possible interpretations, X is said to be valid. When I ask about the predicate, Father Ali or Father Ali X, when the whole complete or whole research is complete and all the search get the true value for every matching, therefore I will say it's valid because it make matching for all the process. Now the model. What is the model? Model in the Block's word example. The Block's word was a model for its logical descriptions. All of the sentences in the example were true under this interpretation. Model, that means all the descriptions of the problem or the statement, that means it's model. Model is the descriptions of all the states of the problem. Inconsistent, the expression that exists Px and not Px, not found. Why? This is impossible to be true. Because if, for example, this true and this is false, would be false. And if this is false, this will be true. Also, this is not be true, not at all. It's inconsistent because it cannot be satisfied. Good. Under any interpretation of our variable assignments. And valid will be it's true, always true. For example, Px or not Px. This is true or not? True. Why? Because it is true or false, because it's negation of the true will be what? True. Or if it's false and this is be true, or would be true. Always true. Therefore, it is valid. Follows sounds and completes. A predicate calculus expression X logically follows from a set S of a predicate calculus expression if every interpretation and variable assignment that satisfy S also satisfy X. An inference rule is sound if every predicate calculus expression produced by the rule from a set S of predicate calculus expressions also logically follows from S. An inference rule is complete if given set S, that statement S, of predicate calculus expression, the rule can infer every expression that logically follows from S. Now the other objects, unification. Unification, the process of complete matching between predicates or the statements, between the statements on the knowledge. And after search all the knowledge, I get the value or assignment for every object of this statements, and finally I get the answer either true or false if it was a predicate, or I get the value if I ask about the function. Thus, unification This is the process of matching between the matched value in the knowledge base and its equivalent reference. For example, variable, constant, or predicate or function. Predicate, function, or constant or variable will be assigned with equivalent value in the knowledge. After the complete of the interpretation or assignments or the evaluation of this process called unification process. And the unification returned either true if I ask predicate. If the asking was predicate will be either true or false. And if I ask about variable or function, will get this value for variable or value of this function after we get the matching. Unification is another thing for determining the substitutions needed to make two predicate calculus expression match. We have already seen where Socrates in man Socrates was substituted for x, Socrates x, and for all x, man x, that means out loud mortal x. What does it mean? Mean x will be mortal if x is man. This is all the application of modus bonus and the conclusion mortal x. In the inference rule, I think there is two main rules. Only two rules. First one is modus bonus, and other ones is modus bonus and modus tollens. Modus bonus means, for example, P and Q. When it's P, imply a Q. If I get a Q, can I infer P? Or I get P, then I get Q. This is modus bonus. Modus tollens means if I get P, I get a Q. If I get not Q, I will get not P. It's modus tollens. This is two things. This is the main part of the inference rule. And this is produced or invented by Socrates. He said, if I'm thinking, then I will be found. So, thinking, P. Found, Q. That's mean P, if P, imply Q. When P is true, therefore we get Q is true. This is inference rule. If I found P, therefore it's exactly will be find Q is true. This is modus bonus by Socrates. And modus tollens, if I P, then Q. If I found Q, not Q, that's not P. This is modus tollens. Unification and inference rules such as modus bonus allow us to make inferences on a set of logical assertions. Now, scholemization. Scholemization, this means replaces each existentially quantified variable with a function. Remove the existential from the statement. When I remove the existential from the sentence, it will be converted to scholemized or columnization statement that returns the appropriate constant as a function of the sum of the other variables in the sentence. For example, in the expression, for all x there exists y, mother x, comma y. The value of the existentially quantified variable y depends on the value of x. Now, y depends on the value of the x. Because the value of y depends on x, y depends on x, y could be replaced by the Scully function f of x. Therefore, this statement or this predicate will be converted to this column, this like this. Mother x for all x. Mother x. Now, y, because y is there exist, and there exist depends on x. Now, call it is f of x. So, some instance of the expressions. For example, this is an example of the unification process. For x, a, go, y. The substitution of the this statement given by the below. For Fred, a, go, z. Other example, for w, this is variable, and a constant, and go jack, and other for z, a, go, mu, z. In this example, the substitution instance or unification that would make the initial expression identical to each of the other three are written as the sets. For example, Fred x z a. In this example, variable x, Fred, this is Fred. Fred is converted to the x. Variable to the variable y, the Fred to the binding. And wx jack by y. That's mean the converting jack in y. And x interpreted in z, or substituted by z. And mu interpreted by y. In defining the unification algorithm that computes the substitutions required to match two expressions, a number of issues must be taken into account. Two things. First, any constant is considered a ground instance and may not be replaced. Neither can two different ground instances be substituted for one variable. Second, a variable cannot be unified with the term containing that variables. X cannot be replaced by px as the trace and infinite expressions p x. The test of this substitution is called occurs check. Once a variable has been bound, future unifications and inferences must take the value of this binding into account. If the variable is bound to the constant, that variable, now constant and variable, that variable may not be given a new binding in a future unification. That means when I get this value for some variable, I get matching between variable and constant, and assign this constant to this variable, in the future must take into account that this variable not changed in other variable, because it's fixed to this constant and cannot change this value of this variable. If a variable x1 is substituted for another variable x2, and at later time x1 is replaced by a constant, then x2 must also reflect this binding. Composition of unification substitutions. Now we will talk about the contacting or concatenation or substitution or compositions of the sentence from two or more sentences. If I get two sentences, the first sentence is called S, and second sentence is called S. Are two substitution sets, then the composition of S and X bar, written as S calculated by with S bar like this, is obtained by applying S bar to the elements of S and adding the result to S. Good. Example of composition of the following three sets of substitutions. This is three statements. This is first statement of substitution. This is second statement of substitution, and this is the third statement of the substitution. Composing, for example, composing the third sets, this set that with the second set and this. Composition between this and this. Now get AX, why AX? Because it is AV in this substitution statement. And in this statement, V substituted by X. That means A is substituted by X. Put it in there. This is one. And we put this and with this. Good. Now, composing this results, this with the first set, this. Now, composing this with this. This means A X, that means AXY. This is X, and this is X, this is AY, this. And AX, AX. Now, AV, this is AV. Now, FBW, WWZ, that for FBZ, FBZ, because FB to W, W for Z. Now, FB to Z, this. And this is named FBW and FBW. Good? Other definitions for the unification are the most general unifier. Most general unifier. If S is an unifier of expression E and G is the most general unifier of that sets of the expressions, then for S applied to E, there exists another unifiers such that ES equal EGS, where ES and EGS are the composition of unifier applied to the expression E. Now, we define the resolution. The resolution with the logic representation, a process that often requires packet tracking to find all possible interpretations. Resolutions, that mean when we use, for example, we use a function and we call in particular functions. And when we reach inside this function, we need to use the same function. We will call it again by another arguments. This is called permutation or resolution. Unification is important for any artificial intelligence problem solver that uses the predicate calculus for the representation. Unification specified conditions under which two or more predicate calculus questions may be said to be equivalent. We next present pseudocode for function unify that can compute the unifying substitutions between two predicate calculus expressions. Unify takes the arguments two expressions in the predicate calculus and retains either the most general sets of unifying substitution for the constant whole if unification is possible. Now this is mean I will get example that will explain how I can use the unification process. Unification, that means I ask something and I will look in between what I ask and what I say or find in the searching process in the knowledge base and matching between them. Finally, I get the results of the matching or assignment of the matching. This is the unification process. And I will get either it is true or fail. Where it's true and where fail? When I complete the search and I found what I'm looking for and get the whole matching between what I ask and what I'm looking for, this is complete. Okay, this is true. But when I'm looking for, there is something wrong, either not matching or complete the searching process. I cannot get what I need, therefore I get failed. Good? It is defined as the recursion function. First, it recursively, the recursion process, it recursively attempts to unify the initial components of the expressions. If this succeeds, any substitutions returned by this unifications are applied to the remainder of both expressions. These are then passed in a second recursion. Now we call other. Call to unify, which attempts to complete the unification. Now I will continue with the recursion. But when can I stop? The recursion stops when either arguments, this is two conditions will make the process will be stopped. The first thing, either argument is a simple predicate, functions, then constant variable, or the elements of the expressions have all been matched. Good? This is two conditions that make the process stop from the loop. For example, we next present the function unify. Now, we will use the process of the recursion and implement in the operation in the unification process, and will be implemented by using the pseudocode that this algorithm represent the process of the unification, and this pseudocode use the operations of recursion. Now, this is named function unify expression 1 and expression 2. Now two expressions, I want to unify them. For example, father X or father X and Muna, for example. This is expression 1. And expression 2, father X, Y. You get what? Begin case. This is case either this or either this or this or either this. Both E1 and E2, the first condition, are constants or the empty list. Now, if get this, it will be if E1 equal E2, the same expression, then return 5. There's nothing. and else return false. Good. The first thing I will do to check if the expression 1 or expression 2 constants. That means, for example, Ali, Ali. This is constant. If the expression 1 constant Ali and Ali is nothing. And we do not need to complete the looking for or the searching. Now close it, fine, but not fail. Otherwise, it's not the same constant. For example, Ali Muna. I ask Ali. I'm looking for Ali and I found Muna. Ali is not equal Muna. That is fail. And the share fail. This is the first one. The second, if A1 is variable, that for example, X. Because X, this variable, that means I must looking for value assigned from the knowledge base to this value X, or to this symbol X. In other words, I must get the value of X by looking for X value in the knowledge base. A is variable, that means if A1 occurs in E2, their return false. Or return E2 and E1. That means E1 is other variable or constant that substituted what I asked E1 with the I found variable or constant or a predicate or something will be substituted by the A1 and written E2 E1. That means E1 substituted by E2. And if E2 is variable, now E2 is occurs in A1, then the return false, else A1, E2. That means E2 substituted by A1. Either E1 or E2 are empty, their return false. There's nothing, because 2 empty. Otherwise, nothing. All this and this. Begin. HE1, first element of E1. I will divide the first expression, because I took expression. I divide the first expression because maybe the first expression is a predicate. Predicate must be divided to its components. For example, father and Ali and Muna. This is 3 things. Father is symbol. Ali is variable or symbols or constant. And Muna also. Therefore, I divided it for that HE1, first element of E1. If E1 is father Ali Muna, H1 will be the first element, HE1 will be father. H2, first element of E2. If E2 is predicate or function, I will get the first thing of this function or the predicate and call it E1. Now, recursion. I will make the substitution between the first string of the first element or first expression and the first string or symbol from the first expression. For example, E1, father XY. E2, father something. I will get first thing father from the expression 1. And expression to father, what is the first thing? Father. And I will make the unification between father and father. Father and father. This is called recursion. This will call this again. This is called function again. This process is recursion. Recursion in other arguments. And continue. Repeat the process. When we reach this another time, other recursion. And two things or two conditions will make the stopping of this operation, the recursion process. What is two things? The first things, I get the matching will stop the recursion. The first things. The second, I complete the recursion and I cannot find any new things in the substitutions. That means I finish the searching in the knowledge base. Nothing in the knowledge base. And in this times I stop the recursion. But two things. And other things, substitution one, fail, then the third fail. And E1 apply substitution with the rest of E1. Or T2 substitution with the rest of E2. And continue. Now, example of the unification process. For example, yes, I say this predicate. If I ask unify in this predicate, in this algorithm, if I ask or use or implement, I will implement a previous algorithm. And I ask the algorithm this, unify parent X, father X, and mother fill, parent fill, father fill Y. If I ask this some things. Well, the first thing, unify first elements and apply. Now, if we get unified parent, unified parent with parent. Parent with parent. You remember we will get the first, because this is all this. This E1. This is E1. And this E2. E1, the first things of the E1 is parent. And first things of the E2 is parents. Good? Now get the first things parents. With the first things and make the unification. Therefore I get unification parents. Remember the algorithm. It will return y. What's the return? Return pi. And come back or go back to the algorithm. Now, unification between X, because I remove this and remove this, remove parents and parents, I get X father, X mother pill, and expression 2 without parents pill father, bill, Y. Now, The first thing, what is the first thing? X. Second thing, build. بدأ يشوفوها ولا ما يشوفوها؟ حروف يشوفوها ولا ما يشوفوها؟ نعم ها اي يشوفوها بالملزمة عندكم. فأنا هذا عندي X. First thing is X and build. X build. X build. Return, what is return? Unification, because it is X is variable, build is constant. What does the rule say? Rule say will be assigned this constant to this variable. That means X will be built. Return the substitution. X substituted by build. Return to the main and substitute it by X by build will be like this. X will be built here. Build, say the same build and build. Well, now the first thing, father build. Here, father build and father build. Substitution between father build and father build, because father and father is return 5, because constant is constant, and build is build return also 5, and continue. Good. Now ناخذ some الساعة 10:30. لا ساعة نكتب وراك المحاضرة.